Let's start by defining a special number that we call Euler's number, and we use a lowercase e to denote this particular number. It's a really odd number in the sense that it's defined as what we call a limit. So we look at the expression 1 plus 1 over n to the power of n. And as we allow n to get really, really big, so that means as we allow n to go towards infinity, this particular expression tends towards some number that we call Euler's number. To give you a rough idea of what the value of e is, let's try to substitute some numbers into this formula. Let's begin with the number n is equal to 1. If we substitute n is equal to 1, we're going to get 1 plus 1 to the power of 1. And this is equal to 2. Next, we might try n is equal to 10. And from here, we may want to pull out our calculator because we're going to have to deal with that fraction and that exponent. And if we use our calculator, we should get a value that's roughly equal to 2.5937. Now we could make the value of n even bigger. We could try next a value of 1,000. And once again, you could try plugging this into your calculator. And in this case, we get a number that's roughly 2.7169. And I'm going to choose a really large value next. I'm going to choose the value of 1 million. And if we were to substitute that into our expression, we would get roughly the number 2.71828. So you can see that as the values of n are getting larger and larger, the right-hand side is actually tending towards roughly 2.71. And that is about what Euler's number is. So let's just write that in here. E is pretty close to the number 2.71. Now, based on what we saw earlier, it's not really immediately obvious why we care about such a number like Euler's number. This is something I really can't motivate in pre-calculus, but it does become a bit more apparent in calculus. It turns out that this number just happens to be the best choice as the base for an exponential function. Since e is roughly equal to 2.71, it's a real number, and we can define an exponential function as follows. We might say the natural exponential function is called e to the x. So here we take that special number called Euler's number and we use it as the base of our exponential function. This leads us to the following definition of the natural exponential function. Like we said on the last slide, if we decide to use the base e for our exponential function, we get the natural exponential function, which we call f of x equals to e to the x. Since e is a real number, when we make the substitution of x is equal to 0 into this particular function, we're going to get the number 1. So the point 0, 1 is always going to be on the curve e to the x, and it's going to increase as we move right, just like our usual exponential functions, and it's going to decrease as we move to the left and get closer and closer to the horizontal asymptote of y is equal to 0. So as you might be able to see from the graph of e to the x, the domain of this function is going to be all real values. That is, x is allowed to be on the interval negative infinity to positive infinity. If we have a logarithmic function with base 10, it's often called a common logarithm, and we usually omit the base 10. Now that is, if we have something that looks like this, log base 10 of x, we often disregard the 10, and we write it just as log of x. So if you do end up seeing anything that looks like this, it's understood that the base is equal to 10. Just so you can see a couple examples of the common logarithm, let's evaluate the following two expressions. First one, log of 10,000. We can rewrite this as log of 10 to the power of 4. Now remember that if the base of our logarithm and the base of the power inside of our logarithm are the same, then they're going to undo each other and leave us with whatever the power is. and that is the number 4. Next, let's take a look at log of 1 over 1,000. We can rewrite this as log of 10 to the negative 3, in which case we're going to get a final numerical answer here of negative 3. Now a question might arise. We might ask ourselves, we know about Euler's number, e. What happens if we use that number, e, as the base of our logarithmic function? This is how we come to the notion of the natural logarithmic function. If we do decide to use Euler's number as the base, then we get log base e of x, and we get what's called the natural logarithmic function. Just like all of our other logarithmic functions, it is going to pass through the point 1, 0, and it is going to have a vertical asymptote at x is equal to 0, and it's going to gradually increase as we move to the right, and decrease as we get closer and closer to 0. So as you can see from our graph, the domain of the natural logarithmic function is everything bigger than 0. When it comes to writing the natural logarithm, we often don't write log base e of x. We tend to prefer a different notation, ln of x. Now don't be fooled, this does not mean 1n or in, this is ln of x. And why we have this notation is a little bit of a mystery. I was trying to dig up why we have this notation. I thought maybe it was French, we would have like logarithm naturel. But it seems like it might have just been a mistake. Someone was writing L of x or Lg of x instead of log, and it ended up turning into ln of x. So a bit of a weird reason why we use this notation, to be honest. One thing that is important to note is that the function e to the x and the function ln of x are inverses of each other. Let's take a look at a couple properties of the natural logarithm. The first one is that the natural logarithm of 1 is equal to 0. Also, we have that the natural logarithm of e is equal to 1. The next two properties come from the fact that e to the x and ln of x are inverses of each other. This means if we go and take the composition of f composed with g, well, this means everywhere we see x in the function f, we're going to substitute in ln of x. So this means we get e to the ln of x, and since these two functions are inverses of each other, the composition should give us x. And this leads us to our first inverse property, and that is e raised to the power of ln of x is equal to x. The second inverse property comes from doing the reverse composition, g composed with f. So in this case, we're going to get ln of e to the x. And because these two functions we know are inverses of each other, this should give us a value of x. And so this gives us our second inequality to be on the lookout for, and that is if we ever see ln of e to the x, this must be equal to x. Let's take a look at a couple quick examples to illustrate the last slide. So the big thing to remember here is that the natural exponential function and the natural logarithmic function are inverse functions. So that means whenever we see e raised to the power of ln, the action of taking the exponential followed by taking the logarithm, or vice versa, they're going to undo each other and leave you with whatever the result is. In our case, the result is square root of 3, so that's going to be our final numerical answer. Down here we have ln of e to the pi. Once again, the act of exponentiating pi and then taking the natural logarithm of e to the pi, we're going to undo those two operations, and we're going to be left with just pi. An alternate way of thinking about this second equation is remember that ln is really log base e. So that means we're thinking about multiplication by powers of e. How many steps do I need to take in order to get to e to the pi? Well, I need to take pi steps. For the last bit of this lesson, I want to talk about the domain of logarithmic functions. Now recall that the domain of ln of x is x has to be greater than 0. And that's because we have a vertical asymptote at x is equal to 0, and our function ends up being over on the right-hand side of our xy plane. So this implies the inside part of our natural logarithmic function has to be greater than 0. And of course, this is going to be true for any logarithmic function in general. Let's use the information from the last slide to determine the domain of the function f of x equals ln of 10 minus 3x. We know that what we have to focus on is the inside portion of our ln function. We would like 10 minus 3x to be bigger than 0. Otherwise, we're going to get negative values inside of our ln function, and it's not going to be able to compute those negative values for real numbers. So first we could subtract 10 from both sides of our inequality, and then finally we could divide by negative 3. Remember that this division has the effect of flipping our inequality, and we get x must be less than 10 over 3. Plotting this on the number line, we would put an open circle at 10 over 3, and we want all values that are less than 10 over 3. This is going to lead us to the following interval notation, negative infinity up to 10 over 3. All right, my little epsilons, stay positive.